Good evening, everyone. Welcome to week 12 problem solving session. My name is Bhabyadeep Rai, and this is the problem session for the final week. So, there'll be one additional session after this that will be on Thursday, same time 6 p.m. to 8 p.m., which will be more of a summary session where I'll be explaining some of the recaps, okay, of the entire course, okay, and from top to bottom. So that might help in the upcoming exams also. So if you have any doubts, then please make sure you attend that. Meanwhile, so this week's topic is space complexity. It talks about classes like before we talked about time complexity. Now we are talking about how much space a particular problem actually requires. So as always, before we embark on the content of space complexity, we'll be solving few of the questions handpicked from the previous assignment. Okay, that is week 11 assignment. So okay, so here's the first problem. The problem can be stated as follows: consider the language half click, okay, which consists of a graph, okay, with specified amount of vertices and edges, specified vertices and edge set, and G contains a click of size V by 2. Okay, pick all the statements that are known to be true. Okay, here known is an important word because as seen before, the problems in complexity theory need not always be said that it is true or false. For example, we cannot say that, oh, it's true that p equals np, or it's true that p is not equal to np, or it's true that sat has a polynomial time algorithm. We cannot say that, and we cannot even say that it's false because of the fact that it is not known as of now. Okay, now first, so which of these are known to be true? Okay, so they are talking about half click. So first, let's talk about click. Okay, before even we look at half click. So click is the set of all g comma k, okay, graph such that a graph g contains a click of size k. What does size mean? Size means the number of vertices in the particular subgraph. So what is the click? Click can be summed up as a subgraph which is complete. What is an example of this? Example is so yeah, so this graph, okay, what is a complete graph? What is a complete graph? A complete graph is a graph where all the vertices are adjacent to each other, all of them are connected. Okay, now additionally, if we take a smaller set of vertices and look at that smaller set of vertices, and all the vertices are adjacent to each other, then the graph is said to be, then the subgraph itself is said to be complete, and such a graph is subgraph is called a click. For example, if we look at these four vertices, and you can see that all four of these vertices are adjacent to each other. This is adjacent to this, and this is adjacent to this, and so on. Is it not? Right. So here you have a click of size 4. Now here too we have a triangle, right? This triangle is actually called K4, right? If this was a graph, but it is a subgraph right now, so we shall call it a click. It is a complete graph on on 3 vertices. So here we have a click of size 3. Okay, this is a click. Now the problem of click detection. That is, given a graph, is there a click there? Is there a click of a particular size there? That is a huge problem which we are trying to solve. Why? Because that particular problem is actually NP complete. So this problem, click, okay, given a graph, is there a click of size k? Okay, this is NP complete. So this is already a very difficult problem. So we cannot really expect to easily find a polynomial time algorithm for this, right? So now what we are talking about is a variant of click, okay, which we are calling half click. As the name suggests, what may it be? It does not take a k this time, okay? It does not take a k this time. It says any graph G give me, and I'll tell you whether it has a click of size v by 2, which is the half of the number of vertices, okay? So what is half click actually? Half click is just a problem click where k equals size of v divided by 2. That's all. Okay. Now the problem says, okay, first let's see, is half click in NP? That is what they are saying. Is half click in NP? Is half click in NP? Let's is it in NP? This is the first question. And the answer is yeah, okay. So let's try to answer that. So how do we show that something is in NP? Either we give it a non-deterministic polynomial time Turing machine, or what can we do? We can say that there is a polynomial size certificate. If the answer is yes, okay, for a given input, let's say the answer is yes, then there is always a small size circuit. Okay, there is always a small size circuit, certificate, such that the certificate can be verified in polynomial time. So there is a polynomial time verifier for this, right? So here we can do the same thing. Now, in simple words, what does that mean? I can give you, if you want to check whether there is a half click or not, let's say, and I tell you the answer is yes, there is a half click. How do I convince you? I tell you, I claim that I can give you a certificate certifying that the click is there, and the certificate is small. And you ask me how can I achieve that? So what I'll do is I'll do a very simple thing. I'll just give you the vertices that form a click, that form a half click, as where the number of vertices is n by 2. Okay, so that form a half click. So what do I do? The answer is yes, and I give you a certificate. Certificate is what? It is the vertices that form a click of size v by 2. Okay, and what is the size of the certificate? What is the size of certificate? What is the size of the certificate? Well, there are at most size of v many vertices, and the click is of size, well, anyway, v by 2, right? And the number of vertices which forms the click will also be v by 2, because that is what size means, right? The size of v by 2, which is linear in terms of the input. It is some order of the input, which is the graph given to us. So it's fine. It's polynomial on input. Okay, so the size is small. By small we mean polynomial size based on the input. Okay, next is, can it be verified easily? Well, if it exists, okay, then certificate can definitely be found. Certificate definitely exists. Definitely exist. And what does the verifier do? Verifier, okay, for each vertex, okay, checks if it is adjacent to um, v minus 1 other vertices, right? So how much time does it take? Well, for each v, okay, a vertex v in v, how many vertices do I need to compare with? The v minus 1 other vertices, right? Size of v minus 1, which is something like order v square. So this is again polynomial on the size of the input. So the verifier runs in polynomiality. Finally, if the click does not exist, if that half click does not exist, then such a certificate can never be found, right? Because the certificate I'm giving you itself is the set of vertices that forms a click, but now I'm saying that the such a click does not exist itself. So that this verifier, you can never fool the verifier. You can never fool the verifier. So yeah, half click is in NP. Is in NP. Okay. Now half click is in P. Let's think about that question for a while. Okay. Half click is in P. Is this true or not? Now let's try to come up with the simplest algorithm for it. Okay. Let's try to come up with the simplest algorithm. What I do is, okay, we want to look for a click of size half of the size of the graph, okay, which is number of vertices divided by 2. What I'll do is go across all sets of vertices of size, what is the size? V by 2. Go across all the sets of vertices of size v by 2 and check if they form a click, right? All vertices of size v by 2 and check if they form a click. But how many such number of such subsets is? What is the number of such subsets? It is, for all the vertices I'm picking the size of v by 2, which is, say the number is n, then n choose n by 2, and this is already very very large. If you try to approximate it, it will come to some n factorial. Okay, even if you do the high school method of expanding, you know, these binomial coefficients, right? You'll see that it is close to n factorial, and which is itself exponential. It's very bad. It's 2 to the n log n. Okay, and this is exponential. This turns out to be exponential, and therefore it seems to be that, you know, half click is a much more difficult problem. It seems to be that way. Okay, now we'll continue. Oh, hi Bhuvana, I'm audible?
Yes, sir.
Oh, okay, good. So I'll just quickly recap. So we are looking at week 11 assignment question 5. Okay, now the language given to is half click. Okay, G is a graph and we need to check whether it contains a click, okay, of size v by 2. What is a click? A click is a subgraph. Okay, a click is a subgraph of the graph which is complete. What is meant by complete? All the vertices are adjacent to each other. Now here I have a graph, okay, and for example it has a click of size 4, because here I can see these 4 vertices, all of them are adjacent, they form a complete graph, okay, but still it's a subgraph. So instead of calling it a complete graph or calling it a complete subgraph, I'll call it a click, okay. In other words, it's just a complete subgraph. So similarly here, these 3 are adjacent to each other, they form a complete graph on 3 vertices, but since it is a subgraph of the bigger graph, I'm calling it a click. So it is a click of size 3, okay. Now so what is the click problem? Click problem is given a graph and a number k, okay. I need to check whether graph contains a click of size k or not, okay. And for example, if this is the graph given to us, this is the g given to us, and let's say k is 4, then my output will be yes, it contains a click of size 4. But let's say the k was 5 and this was my input, then I would say no, because I don't see a click of size 5 here, okay. But the click problem is incredibly hard problem. It is NP complete. You might have seen in the lectures that click is very hard. It is NP complete, okay. But what does the question tell us to focus on is something called half click. Now what is half click? Half click uh, is the input is just given a graph, okay. We are not given a key, but the problem is we need to check if there is a click of size number of vertices divided by 2, or half the number of vertices form the click. Now or in other words, we can think of half click as click only, but where k is equal to size of vertices by 2, right. So is there a click of size? This number of vertices divided by 2, or half the number of vertices. So this is a problem, and they are asking these questions like what is the status of half click? Is it in NP or is it in P? Is it does 3-sat reduce to half click? Does click reduces to half click, and so on? Okay, let's look at the first one. Half click is in NP. The answer is yes, because to show that something is in NP, we need to show that a small certificate exists that can be easily verified, okay. And so I tell you that okay, a click exists there and you are not convinced. So how do I show it? For example, in this graph you are not convinced that there is a click of size 4. How do I convince you? Well, I give you each of these vertices, and let's say they are labeled 1, 2, 3, 4, 5, 6 and so on. I tell okay, 1, 2, 5 and 6 form a click of size 4, and then what you can do is you can check across themselves that okay, all these vertices among themselves they okay, I made a mistake, okay, but anyway, all these vertices among these themselves they are adjacent to each other. So what is the size of the certificate? Well, I'll give you a click of size what, v by 2. That's what you're looking for. So and this is quite small. This is smaller than even the size of the graph. It is linear on the input side, so it's still polynomial on the input side. Size of the certificate is good. Next I need to check whether the verify here does not take a lot of time. It takes only polynomial time. So so the for each vertex, okay, in the certificate, in certificate C, it checks if it is adjacent to, okay, and let C minus 1 other vertices. So this will be for each vertex in C. For each vertex in C, I need to check across other remaining C minus 1 vertices, right? So it's C times C minus 1, and each of these are at most size of V, so it is order V square, which is still polynomial on the input size, because the input is the size of the graph, okay, which is like n square or something, if given as an adjacency matrix. Okay, so we can easily give you a certificate and you can easily verify it. So half click is in NP. So that is the first conclusion. So part A is correct. Okay, now part B, that is what I was explaining. So the question is asking whether half click is in P. Can we hope to say that we can give a polynomial algorithm, polynomial time algorithm to test this? So what is a simple way to test it? Given a large graph, okay, what I'll just do is I'll go across all sets of vertices which are of size v by 2. Okay, because I want to check whether there's a clique of size v by 2, size of v by 2. So I'll go across all such subsets, and if a clique exists, then I'll definitely find it, right? Because I'm going through all of these subsets. But how many such subsets do I need to look into? Number of such subsets is v choose v by 2. Out of v many vertices, I'm choosing v by 2 many vertices, and which is n choose n by 2. And if you try to resolve it, then you'll see that it's order n factorial, which is exponential. It's very bad. So the naive attempt shows that okay, the trivial algorithm that I'm trying to use does not work for it. Okay, so we'll leave it at that. So maybe it is in P, maybe it is not in P. Okay, maybe it's, let's say right now we cannot say. Next question it asks is 3-sat reduces to half clique. Okay. Next question it asks is clique reduces to half clique. So if we want to attempt each of these reductions, probably we have a better chance trying to reduce from clique. Probably we have a better chance reducing from clique, because 3-sat, the input to a 3-sat is a circuit, and then I need to transform it into a graph and then convert it to an instance of half clique, which is sounds a bit complicated. And furthermore, if it is shown true, if clique reduces to half clique, we already know that 3-sat reduces to clique, because clique is NP complete and 3-sat is in NP. Actually, both of them are complete, they reduce to each other. But we already know that 3-sat reduces to clique, and if we have that clique reduces to half clique, it would mean that 3-sat would reduce to half clique also. So both these options would be true if the bottom one is true. So let's attempt the bottom one. Let's attempt clique reduces to half clique. Okay. And also, if clique reduces to half clique, what would this show? If shown true, firstly we have this. If shown true, another thing is that since clique is NP complete, we have half clique is NP complete. These are the two conclusions. So not only these two become true, but the fact that NP becomes NP complete means that, the fact that half clique becomes NP complete means that half clique is in P should not be true. Because if it was in P, if a NP complete language is in P, then P would be equal to NP, which is a contradiction, right? So that is what we are going to attempt. So let's try this D. Okay, clique reduces to half clique. Okay, now how do you do this? So what do you want to do? Reduction is transforming one problem to another problem. What is the input to the clique? What is the input? Input is a graph G and an integer K. K is a natural number. Okay, and what is half clique? Input is a G. So now what we want to do is we want to say that if you can solve half clique, you can solve a problem for clique also. Okay, so this is what the reduction is like. If I can make a clique solver as follows: input I give G and K, a graph and a number K. I do some surgery on it, okay, and call it sigma, and this will give a new graph G prime. Okay, input is some G prime, okay, graph, and this G prime will be fed to a half clique solver. Okay, and if there exists a clique of size G prime by 2, half the number of vertices, then it means there is a click of size k also. The click solver will say yes, and if the algorithm inside will say no, then the outside algorithm will also say no. In other words, if there is a half click solver that solves the problem in polynomial time, then the entire click solver will be solved in polynomial time. Will solve the problem in polynomial time. So what we want to do is we want to find this magical transformation that will turn gk to g prime, and any answer to half click will give an answer to click. Okay. Now let's see. Okay. So we what we'll do is the reduction sigma. Okay. What does it do? It takes a g and k and it will give another graph g prime. That is what we are seeing now. So here's how sigma works. Okay. So let's look at different cases. First, let's say the input to this click solver, okay, the k to the click solver is already number of vertices divided by 2, as is exactly equal to. Then the problem of half click is identical to click, right? Whenever k is given as number of vertices divided by 2, we are asking whether there is a click which is half the number of vertices, of size half the number of vertices. Then what will I do? Simply set g prime to be g, because g prime will tell whether there is a click of size half the number of vertices or not, and then it will say yes. Then obviously the answer for the bigger graph, the original graph, will also be yes, because the question we were asking was same, and the graph we are feeding was also same, is also same. Now let's look at other cases. Say k is less than number of vertices in G divided by 2. Okay. Say k is less than number of vertices in G divided by 2. So what does it mean? So you have the graph G. Okay. Now what you are doing is you're asking if there is a click of size k, and this is a complete subgraph, and this is click of size which is strictly less than v of g divided by 2, strictly less than this. Okay. Now what do I want to do? Okay, I want the answer to be yes, there is a and see, the question is giving a k which is it's something like 10 here and k is 3 here, because 10 divided by 2 is 5 and k is 3 here. Example. Okay, is there a click of size 3? Something like that, when the size of the graph is 10. We want to transform it into another graph, so that if there is a click of size k, then there will always be a click of size half of the size of the graph. How do we achieve that? That is the question. Well, the beauty of reduction is that we can transform this G into a G prime and add more vertices and edges and so on to it. That is exactly what we are going to do. What we are going to do is we are going to add vertices to this G and form G prime. Okay, we are going to add vertices to this G and form G prime. And how many vertices are we going to add? We are going to add so many vertices that the click size is half the number of vertices. Okay, and what we are going to do is we are going to attach it to every other vertex in G and every vertex with itself. This is the idea, and so on. Now what happens? Since this is a complete graph, right? Small complete graph, this is a click. Now additionally, it is also adjacent to every vertex in this new set of vertices, and these new set of vertices are also adjacent to each other. So this will form a bigger click. This part will form a bigger click. Bigger click. And how big should this click be? This bigger click should be exactly half the number of vertices in G. G prime. Getting it? Because this is G prime. And now I ask you the question, oh, is there a click of size, V of G prime by 2? Okay, is there a click of size V of G prime by 2? Then you'll say, yes, there is a click of size V of G prime by 2, number of vertices in G prime by 2, if and only if there is a click of size K. Okay, so what I'll do is now, how do I achieve that? Well, so what I want to do is, I want to make sure that after adding these vertices, okay, after adding these vertices, my graph is of very large size. Okay, so firstly, what do you have? K is less than V of G by 2 means 2K is less than size of VG. Right, I'm just multiplying to that side. So 2K is strictly less than VG. So what does this mean? Vertices of G, okay, the number of vertices in G, okay, is strictly larger than 2K times, or 2 times K. Okay, so since it is strictly larger, there is some gap between them. There's some gap between them, right? Otherwise, it would have been equal. So that gap will say, so let's say, suppose V of G, okay, minus 2K is exactly the size of the gap, is equal to some Y. V of G minus 2K is equal to some Y. Okay, that is the extra gap that we have. Now what we'll do is, we are going to include that gap many vertices, extra vertices. Okay, so these vertices that we added is that gap many. Okay, include Y many vertices. Okay, so this is Y. Okay, Y many vertices. And so what is the number of vertices in the new graph, which is the original size of the graph plus Y. Okay, and what is Y? V of G plus V of one moment, V of G minus 2K. So this is the new size of the graph. So we've made it bigger, okay, by including these. Now, what is the size of the new click that we obtained? So, and this is some 2 times V of G minus 2K, which is 2 times vertices minus K. Okay, and okay, now next, what do you have? Okay, so now what is the size of the newer click? Because we said that this forms a click, right? This forms a click. So we'll give it a name. So we'll call it C prime. Let me call it C prime. This is the new click. So how many vertices does it have? C prime has how many vertices? Originally it was carrying k many vertices. Okay. Now it is carrying k plus y many vertices. So now we are guaranteed a bigger click after including those vertices. K plus y many vertices, and after including that, what is y? Vg minus 2k. Okay. So how much do we obtain? K plus k. Okay, one moment. I think I made a slight. I wanted this to be equal to 2k. One moment. So okay, the click size is some Vg minus 3k. Oh, plus k. Oh yeah, that's right. Vg minus k. That's right. Yeah. So what is the new click size? Number of vertices minus k. Right. And what is the size of the graph we've obtained? Twice the number of vertices in G minus k. So we can already see, okay, that this is the size of the graph G prime. This is the size of the graph G prime. And this is the size of the click. New size of the click, which is V of G minus k. So this is exactly half. And if k is, let's say, if there was no click of size k, then we would not have obtained this. Take note. Right? If there was such a click was not there, okay, such a click was not there, this click was not there, the smaller click was there, let's say, then this would not have been sufficient. Since this click was there, we are saying that there is a click of size k plus y. And because of this, we are getting this value. Otherwise, we would not have got. So therefore, okay, therefore, C prime, the size of C prime is exactly equal to size of V of G prime divided by 2. Whenever k is less than k. Sorry, what am I saying? K is less than Vg by 2. Okay. So far, is it good, Puvna?
Yes, sir.
Okay.
Hello?
Yeah.
Yes, sir.
Okay.
Yes, sir.
Okay. Good. So the final part is actually identical. So I won't dabble it on it too much longer. So that is only when, so number of vertices in G divided by so k is strictly greater than number of vertices in G divided by 2. Then you do the same thing, you have a mismatch, right? So this would imply that 2k is greater than V of G. Now let y be this gap. Okay, understood. Oh, okay, good. Okay, so let this gap be some 2k minus Vg. Okay, and now what you want to do, now what you are saying is, see, what does this mean? This means that the click is very large, right? Click is very large. I want to transform it again so that it becomes exactly half. Now what I'll do is, I'll do the same thing, similar thing. I'll include a y, but this time I'll add isolated vertices. They won't be connected with each other. Isolated vertices. What I'm trying to do is I'm trying to blow up the size of the graph so much so that the click that was originally there, the large click originally was there, in comparison to the size of the graph becomes smaller. How small? Until it is half the size of the graph. Okay, so I'll do the same thing. Now this is y, and here I have a click. Oops. Here I have a click of size k. Click of size k. Here I have a click of size k. And how much do I want to blow up? Well, until again, like it's the size of the click is half the size of the entire v prime. So let's check how to do it. So I want the click size, okay, which is k. Remember, click size is k, and I want k, the click size, to be equal to half of the original of the new graph size, exactly v prime divided by 2. Now what are we saying? We are including y many isolated vertices, which is equal to y y plus v of g, because we are adding these many isolated vertices, right, divided by 2, and which is equal to, what is y? 2k minus vg plus vg divided by 2, right? And oh, okay, we won't simplify further, otherwise there's no use. Yeah, okay. So here we have this. So what does this imply? This implies 2k equals y plus v of g. And what is y? Y is 2k minus v of g. What does this mean? Y is this number of isolated vertices we need to add. What we'll do is we'll simply include 2k minus vg. Y equals 2k minus vg many isolated vertices. Okay, we are including this. Now the graph is so big, but the click size is still same. Remember, the graph is so big that the huge click size, which was more than vg by 2, now becomes exactly half. K equals v prime of g, the final graph g prime. Okay, so keep thus include y equals 2k minus vg isolated vertices. Isolated meaning no edge among them. So that what? K, the size of the click, will be equal to, compared to the new graph, it will be exactly half. And you're done. Because if there is, now note that if the answer is yes, there is a click of size k, then in the original graph I'm saying yes, there is a click of size exactly half. So therefore the yes would give no yes, and no if I say no, the click the there is no click of size k, then there will be a mismatch in the calculation, and exactly half, the click of size exactly half will not be present, so there will be a mismatch. So the answer is yes, click reduces to half click. Okay, click reduces to half click. Now click is NP complete, and 3-sat is in click, so this means that, and 3-sat reduces to click, right? So this means that 3-sat reduces to half click. This is because 3-sat reduces to click, because click is NP complete. So both these answers are true. And finally, half click is in P. This cannot be. Why? Because if half click is in P, if true, then P is equal to NP. If true, then P is equal to NP. But this is not known, right? So the question is asking what is known to be true, but this is not known to be true. Okay, is that fine, Bhuwana? Okay, good. Um, yeah, quickly we'll look at this one. So let me try to complete this part by 7 at least, so that we can move on to this week's content. So you must have seen Sudoku already, right? So the question said, consider a generalized version of Sudoku played on n square by n square grid. Each row, column, and n cross n subgrid should contain number 1, 2 till n square exactly once. Okay, and so on. What is Sudoku? Sudoku you might have seen. It looks something like this. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is what Sudoku looks like, and you have it partially solved with numbers ranging from 1 to 9. Oops. Okay, so this is somewhat what a Sudoku looks like, and the rule is that I need to complete the Sudoku by filling the remaining numbers. Okay, and for example, I put a 1 here, and then I putting a 1 here is not allowed. Why? Because there's already a 1 in that particular row. So you might have seen this. The game is played this way. Okay, it's not a game, it's a puzzle actually. So there's only a single person playing it. So every row has uh, numbers from 1 to 9, and each number occurs exactly once. So you cannot have double times. So what we are looking at is a generalized. Yeah. So what we are looking at is a generalized version of Sudoku. Instead of playing 9 by 9, I'm trying to play n cross n Sudoku. Okay, it could be 10 cross 10 or 100 cross 100 for that sake. Okay, and it's saying a Sudoku is partially filled, and the input to a Sudoku is a G. Okay, and G looks like this. Okay, it can be considered as a matrix, and G is partially filled generalized Sudoku, and you need to check whether it has a valid solution or not. There, I may give you some kind of faulty Sudoku questions, which may never have a solution. You may try so much, but you'll never get a solution. So you need to tell if it has a valid solution or not. Okay. Now here's the first question. Okay. I hope you've already played the game, and I hope the game is familiar with you. So here, if you have 9 cross, and there are 9 columns and 9 rows, and also by the way, even these, okay, even each of these subgrids have that condition that they can only contain each number exactly once. Okay, so this is what they are talking about, the subgrid. Now first they are asking whether Sudoku reduces to SAT or not. Okay, before moving on to the next question, this part, we'll look at this part. Sudoku over a 9 cross 9 input grid reduces to 9 colorability. What is 9 colorability? Okay, what is 3 colorability?
We need to color the edges in such a way that nearby edge does not have any similar colors.
Right. And that is the edge version. And standard, in a standard way, we there is a vertex version also, right?
Okay, sir.
Yeah, yeah. And the edge version, edge colorability is also there. Yeah, like you said, you color edges like this, and adjacent edges must not be uh, uh, colored the same color, right? Similarly, there is a vertex version also. So here, the vertices needs to be colored, and adjacent vertices should not be colored the same color. So something like this is not allowed. It needs to be colored with a third color, green, say, because it is adjacent to another blue vertex. Okay, and three colorability is NP complete. Okay, three colorability is NP complete, and you may have seen it in the lectures. Now, question is Sudoku over a 9 cross 9 input grid reduces to 9 colorability. Sudoku 9 cross 9 reduces to 9 colorability. Question, okay, in other words, can I transform a Sudoku puzzle, which is of 9 cross 9 form, into a graph? Okay, and say that, okay, the Sudoku has a solution if and only if that graph is 9 colorable. Okay, so that is the question, what it's asking. So, surprise, I mean, interestingly, the answer is yes. You can actually transform a Sudoku to a graph. Okay, and how do you do that is color. Okay, good. You take one and assign a color, red. Take two and assign another color, blue. And three and assign a color, green. And assign unique colors, so on till 9. Say 9 is purple. Okay, now the input to a Sudoku is a puzzle. Puzzle P is the input. Now the input here is a graph G. I need to transform that puzzle into a graph G. How do I do so? Okay, so I have a puzzle 9 cross 9 and I need to convert it into a graph. Okay, now the trick here is as follows. In a Sudoku, we are saying for each column there should be a each of the numbers should exactly occur once. Okay, and even in the rows, each of the numbers should occur exactly once, and in the subgrid also, it should occur exactly once. So now what I'll do is I will do the following construction. For each cell, okay, for each cell, so for example, let me call this cell, C11, C12, C13, and so on till C19, C21, C22, C23, C29, C31, C32, and so on till C39, and so on until C99. This is each cell. Okay, for each cell Cij, okay, make a vertex Vij. Okay, now if Vij two vertices and Cij two cells and CKL belong to same column, then add edge from Vij to the corresponding vertices VKL. Okay, I add a edge, not only column, if they belong to the same row or if they belong to the same subgrid. I add an edge between them. Why is this the case? For example, here I have C11, C21, and so on. Okay, and C, so V11, V21, V31, and so on. They will have edges between them, and V41, and so on. They'll all have edges between. They'll form these kind of complete graphs. And not only that, for example, C12, so V12, V13, okay, these guys, and so until V19 will actually share edges among them, and also with V11, right? And similarly, this particular grid will also share vertices with each other, and so on. The idea is that if I want to check whether they are 9 colorable, okay, whether this graph is 9 colorable, I need to assign a red here, then the one adjacent to it I should assign a blue, or some other different color, and V31 I should assign a green, and V21 I should assign an orange, and similarly I can assign a red to V12, and I can assign a yellow to V13, and I can assign red to V19. Now let me color the corresponding cells. So V11 is blue, so C11 I'll color it blue, and V21 is orange, so C21 is orange, and C13 is orange, and V41 is red here. Oh, not here. V41 is here, and V12 is here, and V41, okay, V41 is done. V19, okay, V19 is here, and so on. Oh, okay. Oh, okay. Sorry. V19 cannot be assigned because V19 will be adjacent to this guy, right? So it needs to be assigned some other color. Green. Basically, adjacency represents, okay, two vertices are adjacent, represents that those two cells either share the same row or the same column or the same subgrid. So since they are adjacent, they cannot be colored the same, which means in the same row, if two cells are in the same row, then they cannot be numbered the same. So if I give a proper 9 coloring, then I'll get a proper numbering on this row, because each color actually corresponds to a particular number. So if this particular graph is 9 colorable, can be colored with 9 colors, this would imply that this Sudoku can be solved. If it cannot be solved, it means I cannot have it that in all the rows, all the columns, each number appears only once. So the corresponding graph also means that I cannot uniquely color all the vertices using this rule. Okay. So is this part clear? Bhuwana, can you hear me? Is this clear?
Understood, sir.
Okay, understood, right? Okay, good. So now this Sudoku can be solved, and therefore Sudoku reduces to 9 colorability. So this is correct. Okay. Now Sudoku reduces to SAT. So now Sudoku reduces to SAT. Well, we already know that SAT is NP complete, and Sudoku is in NP. SAT is NP complete and Sudoku is in NP. Why is Sudoku in NP? What is the certificate? The certificate is the solution. I'll give you a solved Sudoku. to you, and you'll just go through all the rows, and you'll go through all the columns, and you'll go through all the subgrids, smaller boxes, and then you'll say, oh, okay, all the 1 to n numbers occur only once, and it'll take how much time? All rows, all columns will be n plus n plus, number of subgrids, which is also n. So it'll take some order n time to verify. And of course, the certificate I give you is of size n square, right? The size of the Sudoku is an n by n matrix, which is of size n square. So it is in NP. It is in NP, and SAT is NP complete, means that Sudoku will reduce to SAT. That is the definition of NP complete, right? All the languages in NP will reduce to SAT, or any NP complete language. So Sudoku is in reduces to SAT. Okay. Okay, it's 7:05. So I'm not sure whether I'll get time to do this one. Okay, I'll move on from this. Okay. If I get time, I'll complete. I'll come back to this question or following question in the assignment. Okay. So this week's content. Okay. So this week's content is space complexity. Okay, yeah, okay, good. So this week's content is space complexity. Now we've talked about how time is important, right? How much time a particular program takes, and we are also interested in how much memory a particular program will consume, right? And that is what space complexity talks about. How and we can characterize the problems in terms of difficulty not only by means of time but also by means of space. Okay. So there we have some classes like L, NL, and so on. So L, what is L? L is all problems computable in logarithmic space. Okay. And what is P? Already we know. And what is P space? All problems computable in polynomial space. And next, EXP is all problems computable in exponential time, not space. There's something called EXP space also, but it's out of scope. But see, these are the mainly these two, L and P space, are space complexity classes. In terms of the space, it takes logarithmic space. Okay. In terms of the input, it takes logarithmic space. Then the problem is in L. If it can be solved in polynomial amount of space, then it's in P space. So trivially, what can we say? Okay, trivially, L is contained in P space. Obviously, if you can solve it in log n amount of space, you can obviously solve it in polynomial amount of space. Right? We'll just use given a polynomial size tape in the Turing machine, we'll just use log n number of cells, how much ever we want. Okay, that order log n amount of cells, and we'll be done. This is trivial. And the question is asking which of the following is true or known about complexity classes. P is contained in L. We'll come back to this. Okay. First, let's see this. L is contained in NP. Okay. Now there is an argument, okay, which says the maximum number of cells visited by a space-bounded machine is exponential. Okay. So the idea is that, but I'll only do this briefly because this is done in the lectures. So if space-bounded machine, so here is a tape of size at most Sn. Okay, and it is space bounded. The machine is space bounded means I cannot use the entire tape. I can use only some S of n many cells. Okay, then what happens is the number of configurations, if you remember the configurations in a Turing machine, is what the state your machine is in and the tape alphabet. How many types of tape alphabet you can have. Now that your machine is space bounded, it's not infinite. Your machine is space bounded, you can have 2 to the Sn. You can assign 0, 1, 0, 1, 1, and so on. How many bit strings of this form can you have S of n? So that is 2 to the Sn many. And okay, or in the beginning, yeah, okay, let's just keep this. And that is, and the head position, right? Head position can be 0, 1, 2, 3, and so on till S of n. So this is head position, and it can have S of n many values. Oh, actually, to yeah, that's right. Okay, S of n many values, and this number of states is always constant for a given Turing machine. It's always fixed. It's not going to change. This is constant. So this is order of S of n 2 to the S of n. So what is that is the result, and what is the theorem? So any S of n space bounded machine. Oh yeah, and since there are only so many configurations possible, the machine can run for only this much time. Because if it runs for more than this many time, it means some configuration is repeated. If some configuration is repeated, my Turing machine is never going to halt. So, and we are only talking about decidable languages, those problems for which there are halting Turing machines. So, this is the maximum amount of time we can have. This is the max time. Any Sn space bounded machine runs for, okay, at most how much time? Order Sn 2 to the Sn. And since 2 to the Sn is dominant term here, you can even say order Sn. Okay, if you don't want to be too precise. Order 2 to the Sn. So if there is a machine that runs in log space, okay, we are asking this question, right? L is contained in NP. This is a question we are asking, right? So here S of n is what? S of n is order log n, which implies that machine runtime, okay, the particular machine which runs in, say, S of n equals via machine M, okay, so runtime of M is equal to order 2 to the order log n, right, by the theorem we just saw. Now if it is order 2 to the order log n, what is 2 to the log n? 2 to the log n is n, right, which is equal to order or okay, let's say order log n can be written as C log n, which is equal to order 2 to the log n to the C and 2 to the log n to the C, okay, because both of these are base 2, we'll just have n to the C, which is polynomial. So M runs in polynomial time. What does it mean? It means for any language A in L, A is in P. It's not just in NP, it's in P. It's even smaller class. So what does this imply? L is contained within P. This means that since P is itself contained in NP, L is contained in NP. Okay. So this is an important fact. Please remember this. Any space bounded Turing machine requires at most exponential to the space amount of time. Okay. So P is contained in L is true. Oh, okay. What? Okay. Yeah. Sorry. L is contained in NP is true. Next, P is contained in P space. P is contained in P space. Okay, let's see. Now let's say some L, a language L. Okay, this is not the class L. Okay, say language L is in P via a machine M, which means M runs in polynomial time. Okay, M runs in polynomial time. Any arbitrary language and M runs in polynomial time. Now, M takes, say, some poly n time for all n, for any input. It takes polynomial time because L is in P via this machine. Okay, otherwise it would not be in P if it would take more time. Now, the idea is as follows. Any Turing machine to move from one cell to another will take at most one step. Right? Moving from one cell to another takes one step. Right? At least one step. Right? So what my machine takes polynomial time. What is the maximum time? Oh, sorry, what is the maximum space? And how is space defined as? Sorry, I did not confirm this in the beginning. Space is defined as the rightmost cell in the tape that you can touch. That is defined as a space. So what is the rightmost cell you can touch? Since it takes at least one step to move to another cell, okay, if it takes polynomial time, say it takes not even polynomial, let me be more specific. If it takes order, okay, not order, let's say it takes n to the c many time for some constant c, n to the c time, then I can, this machine, if it wants to take the maximum number of steps to the right, it can only reach until some n to the c, right? It cannot move to something more than n to the c. Getting it? It cannot move to something more than n to the c. Why? Because the maximum number of steps it takes itself is n to the c. How can it move to a cell that is further away from n to the c? That is not possible because it is time bounded itself, and therefore because it is restricted by time, it is restricted by space also. So it means rightmost cell it can touch is n to the c, which implies space taken in the worst case is at most n to the c many bits. Getting it? So this means that if I have any language in P, the corresponding machine will only take polynomial space. It cannot take more space. Okay. So, and furthermore, this particular machine M is bounded in terms of space by polynomial factor. So M takes, okay, or here itself I can say space taken by M is n to the c, which is polynomial. Since it takes polynomial space and it decides L, this implies L is contained in P space, polynomial space. Since we took an arbitrary language in P, it means it holds for any language in P, which means P is contained in P space. Okay? Clear, right? Okay. So P is contained in P space, and look here, P space is contained in exp. Okay, yeah, good. Next question is P space is contained in exp. Now again, true. Why is this true? Why is this true? Why? Because, okay, because take any m, okay, such that L of m, language of L of m is in P space. So here, what is S of n? The space taken is polynomial in n. So what is the time? Time taken by m. By theorem that we saw earlier, we have exponential in terms of S of n. So order of 2 to the S of n, right? Which is order of 2 to the polynomial in n, which is exponential. So this means m takes at most exponential time. M is an example of a machine that takes exponential time. This means that language of m is an exp, and since we took an arbitrary L, this means that uh, uh, the original machine that we started out with, PSPACE, original language that we started out with, is always contained within exp. Any language you give in PSPACE can always be computed by an exponential time uh, Turing machine. Okay, this is how space and time are related. So this is also done. Now finally, P is contained in L. This cannot be true. I cannot give an immediate justification for this without going too deep and without going out of scope from the lectures. But this is something that is not known, and this is a huge problem. And this is also known as the L versus P problem. And there has been various attempts on trying to resolve this. It is believed that L is not equal to P. Okay, just like P is, it is believed that P is not equal to NP. And similar to L versus NL and P versus NP, this L versus P is another big problem in uh, complexity theory. This is not known. All that is known is the following, that L is contained in P, right? And how do you know this? Because of this we showed just now using the theorem. Now I want to, now we've talked about these classes, so I want to give you a diagram which will help in remembering these stuffs. Firstly, we have L, which is a very weak language. It is contained in NL. NL itself is contained in P. P is contained in NP. Now NP is contained in P space, and P space is contained in EXP. Okay, and by Immermann-Zelepsiny, you might have seen in the course that it is closed under complement, and P is also closed under complement. P, let's call it co-P. Okay, and P is also contained in NP. Whether these are equal or not known, and this is known, and P space is equal to co-P space. This is known, and this is also equal to NP space. Okay, these are the things that are known. So take a look at this diagram, and the exp is contained in NEXP. You can write the non-deterministic version also, but this is the diagram that will help you, visualize where things are. It's similar to, for example, if you remember, regular is contained within CFG, CFL, okay, is contained within context sensitive and so on, and which is contained within recursively enumerable, which is contained under recursive, which is contained inside undecidable. So this is a diagram which will help in remembering, the previous matter. In complexity theory, the left diagram is very important, and these are actually interrelated. For example, you can place regular inside L, and you can place CFL inside NL, and so on. Okay. Anyway, this is a diagram which will help you in remembering. Okay. Now moving on. Question says the complexity class PSPACE is closed under which of the following operations? Union, intersection, complementation, clean star. Well, this is a simple question. Okay. Because PSPACE is such a powerful machine, you can do so much using it. Okay. And let's see. Union. The remaining maybe I'll just do the first two, and remaining you can try. And the answer is yes for all. Okay. Union. So let's say L1 and L2 are two languages which are contained in PSPACE via M1 and M2. Via meaning both takes polynomial space. Both these machines takes polynomial space. So what I do is I need to find the union. What does union mean? Either M1 accepts or M2 accepts or both accept. So what I'll do is define machine M2. Sorry, let me call it M. Define M as follows. I run M1 on tape. Okay, the polynomial size tape I have. Okay, and then okay, and as soon as M1, I also run M2. Oh, what I'll do now is record M1's output, which is either yes or no, on 1 bit, using 1 bit. Okay, record using 1 bit. So for example, here is the tape. Okay, and it starts during M1's run, it starts writing 1011 and so on. At the end, what you do is on the first bit you just record whether it said yes or no. Suppose it said yes, I'll keep a 1 here. Okay, next what do? I just simply erase remaining part of the tape. Okay, actually I don't even need to erase. Yeah, but okay, I'll still erase. Let's say part of tape. I'll erase the remaining part of the tape, meaning this part is erased, and then run M2 on it. M2 on tape. So again I'll run M2, and here I'll run M1. Anyway, it is going to take polynomial time. Why? Because how much space am I using? Space I'm using is maximum between M1 and M2, right? Space taken by M1 and M2. Space taken by M is maximum. Okay, and then except if both accept. Oh, except if one accepts. One of them, at least one of them accepted, else reject. So what is the space taken? It is the maximum between the space taken by M1 and the space taken by M2. Maximum between the space taken by M1 and the space taken by M2, because that is the maximum amount of space you are using. And since both are polynomial, this is polynomial and this is also polynomial, the total space taken is also polynomial. Okay, now union is fine. Intersection, same logic. You check if both accept at the end. Okay, and complementation, clean star. So these two you can try once. The logic is very similar. The main idea is space can be reused, time cannot. This is the main idea. Space can be reused and time cannot be reused. Okay. Moment. Okay. So, okay, yeah, good. So now we'll look at NL and NL completeness. Okay, what is NL first of all? NL. So we know what log space is. NL is non-deterministic log space. Like NP, okay, there are two definitions of NP, right? One definition is there is a non-deterministic Turing machine that runs in polynomial time. Similarly, here we are talking about log space instead of time. So one definition is for any language in NL, there exists a non-deterministic, which means it can make guesses on the way, Turing machine taking log in space this time instead of polynomial time. Okay, this is NL. And another definition, alternate definition, is the verifier definition. Okay, if it is an NL, then there exists a polynomial size certificate such that now there is an efficient verifier, okay, such that the certificate can be verified efficiently. By efficient, now we do not mean that the time taken is polynomial. Now we mean that the space taken is logarithmic. It can be verified in order log in space. Okay, these are the two different definitions. It is recall the definition of NP and compare. It's quite similar. Okay, and like we have P versus NP, we similarly have L versus NL also. This is not known so far. Okay, now what is meant by completeness? NL complete means two things. One is L is NL complete, means that L is in NL, sorry, not NP, and two is all the languages in NL, okay, they reduce, log space reduce, remember, not polynomial. Means that the reduction that you compute, the surgery you do, should be doable in log space. Reduces to L. This is what we mean by completeness. This is also what is called NL hard. If just 2 is satisfied, then we are call it NL hard. Okay. Now, why did I bring all this notation? We'll soon see. Recall the language EDFA. M is a DFA such that L of M is phi. Show that EDFA is NL complete. What is EDFA? E stands for empty, which means the language of the given DFA is empty. M is a DFA and language of M is empty. It does not accept any string. So can you tell me what kind of DFA will have the its language as empty? When will a DFA never accept any string? Never accept anything.
Once it reaches accepted state, sir.
Once it reaches accepted state, wait. Once it reaches accept state, will the language be empty or non-empty?
Non-empty, because it has a string.
Good. So what is empty? it does not reach accept state. It will never reach accept state
Fine.
for, yeah, right, right, good. So language of a DFAM is empty if and only if accept states or final states, right, or final states can never be reached. It is never possible to reach a final state. Okay. Okay, so this is one thing. Okay, this is one idea. Next thing we observe. Okay, okay, oh, okay. First, we also need to show. Okay, okay. Before I do this, we need to show that to show completeness, we need to show that it is in NL, right? We need to show that uh, EDFA is in NL, that the language is empty. Okay, the language is, oh sorry, it can be easily verified that the language of the DFA is empty. So there are two ways to do it. One, okay, I'm thinking whether to do the verifier definition or to do the, okay, I will not do the verifier definition. I'll do the non-deterministic definition. Okay, so how will I prove this? I'll prove this. I can give a non-deterministic Turing machine as follows. Okay, so what I'll do is I'll take the DFA, which looks like this, and so on, and there is a final state like this, or there are several final states. They should not be reachable. How do I do this? Is every time I am in a state, I non-deterministically guess the next state I should go to, either this or this. So let's say I guess to go to this, then I'll choose this path, and let's say there was another path here. So I non-deterministically guess another vertex. How many vertices am I remembering? I'm remembering only one vertex. Okay, so if there are n many vertices, I just need log n many bits to index it, right? Because it's like um, if I have 1, 2, 3, 4, 5, 6, 7, and so on, and n. To encode this in binary, I'll just need log n bits. Log n bits for each state, to number each state. To store it, so each time I'll remember only one bit. I'll forget where I came from. I'll forget where I came from, and that's what I do. So I'll just keep doing this. Okay, and if all of them, if I, oh okay, this corresponds to unreachability. Okay, uh, okay, if okay, I'll do it in the other fashion. Let's say I reach a final state, then I'll say yes. Okay, if I reach a final state, we'll show, okay, we'll show EDFA is in co-NL. Okay, that is its complement, EDFA complement is in NL. What is EDFA complement? It means non-empty. If it is non-empty, some path will reach the final state. So some path will reach the final state. So it will accept only if some path reaches final state. Okay, so this is the idea. Basically, every time you visit a state, on each vertex, non-deterministically guess next vertex traverse the next vertex, non-deterministically guess the next vertex, and what you do is every time reuse space. That is the vertex you are using to remember the previous one. Don't remember it anymore. Forget about it. Move to the next one, and move to the next one, and so on, so forth. If it so happens that you reach a final state, and if it exists, if a path exists, you will definitely find it. If a path exists, you will definitely find it. Then what will you say? You will declare that okay, final state is reachable. So EDFA complement, okay, the graph belongs to EDA. Sorry, the DFA belongs to EDFA complement. That is, the language is non-empty. Okay, and that's what you do. And by reusing the space, how much space will you take? Some log n space, because you are reusing that space each time, that log n number of bits. So here is now this is a non-deterministic algorithm that will solve the problem, and therefore it is in NL. Therefore EDFA is in NL. Okay, one moment. I'll just push it to the next page. Okay, now, right. So so what does this mean? This means EDFA is in co-NL, but by Immer-Menzel-Upsoni. It's a difficult. Okay, I'll just write IZ. It was done in the lectures that NL is equal to co-NL. It is closed under complement. So what does this mean? If NL is equal to co-NL and EDFA is in co-NL, it means EDFA is in NL. Okay. This was because EDFA complement is in NL. Okay. Now we've proved that EDFA is in NL. We need to show it's NL hard. Okay. Need to show EDFA is NL hard. We can do this as follows: by reducing an NL complete language to EDFA. And what is the language? NL complete language. It is the famous problem which is known as path. Path is very simple. It is given a graph G, S and T. G is the graph, S, T are vertices in the graph, such that there exists a directed path from S to T. This is also called reachability. Can you reach the vertex T, the target, from the source? Okay, so this is NL complete, as you may say. This is canonically complete, by the way. So this is NL complete. Okay, for example, this graph okay, and this is S, this is T, and there exists a path, right? I can go through this path. I can go through this path. So yes, the answer is yes. Given S and T and this graph, the answer is yes. Now, I think you can already see the similarity between the DFA and this. Okay, what we are going to do is as follows. Again, we are not going to talk, because we are talking about emptiness. If you are talking about non-emptiness, then directly we are talking about start state and final state is T, and then we just translate it as follows. What we do is we will talk about no path. What is no path? GST, no path from S to T. Now clearly no path is a complement of path. No, complement of path is nothing but no path. Now, which means no path is NL complete. Why? Because it is complement and NL is closed under complement, because NL equals co-NL. Since it is closed under complement, even if I complement it and the complement version is the same, is not the same, it belongs to the same class and it is complete also. Okay, so now we are finally ready to finish the proof. Now here is the observation we made, right? That if the language is empty, then the final state can never be reached. Final state can never be reached. Compare it with no path. No path means that T, the target vertex, is never reached, right? And here final state is never reached, so it's the same thing. So here we want to say that no path reduces to, in log space, reduces to EDFA. What is the input to no path? G, S and T. What is the input to no path? G, S and T. What is the input to a DFA? A DFA M, and that's it. What we are going to do is, given G, okay, given G, construct DFAM so that if U V is an edge in G, then make a transition delta U on any arbitrary, say 1, is equal to V. U and V are states. Okay. Now, for example, if you have a graph like this is the given graph, and here is S, here is T. I am considering it as a DFA and make S start state, make T final state, and this is all. So T is made the final state, okay, and S is made the start state, okay. Now, and on seeing a 1, if there is an edge on seeing a 1, then I'll move to that particular state, corresponding state. Now, what I'll do is, if the language is empty, the final state will never be reached. Let's say the final state cannot be reached. Let's say the final state cannot be reached. Like this. Final state cannot be reached. If final state cannot be reached, then it's empty. Okay. And since the original graph also looked like this, it means there was never a path. There was never a path from start to T. So the answer will be yes. There is no path. But if let's say the final state can be reached, it means in the original graph also there was a path from S to T. And since there was a path from S to T, no path is false. So there exists a path from S to T. So this implies no path reduces to EDFA, but mainly what happens, EDFA is NL hard, therefore EDFA is NL complete. Okay, so checking whether a DFA is empty or not is NL complete. So it's 7:48. Okay, was this clear, Ona?
Yes, sir.
It was clear, right? Any questions?
Yes. No, sir. No questions, sir.
Okay.
Sir, I have one doubt, sir.
Sure.
If I have some doubts in assignment, some old assignments, assignment 2 and 3,
Yeah.
um, can I ask the question, sir? How to ask them, sir?
Sure, sure. You can ask me the question. I'll give you my email. Is that fine?
Okay, sir. I will mention it this.
Okay. I'll type it out right now. One moment.
Okay, sir. You
Uh,
tell me, sir. Yes, tell me, sir.
yeah. Wait. I am typing it. Can you see it
Okay.
in the chat?
Yes, sir. I can able to see here, sir.
Okay. CS21D 200 at smil.iitm.ac.in. Okay. Note it down because as soon as if we end this meeting, then it'll go away.
Okay, sir. I will note down, sir.
Okay. I'm giving you an alternate email also. So these two. Okay. Feel free to drop an email in any of these two. Okay. Have you noted it, Bona? Okay, good. Okay. So, yeah. So that is there. So I think the exams are approaching. So you might need some doubt clarifications. So feel free to drop me an email there, and I'll reply to you as soon as possible. When is the exam date? Exactly. Good. Okay. When is the exam date? 20. Okay. So today is 16th. Oh, okay. There are 4 days. Okay. So, okay, there are 4 days for preparation. Um, okay. So, we don't have enough time, but um yeah. So these are very simple questions. This four is simple, and this five. Okay, four is very simple. You can try it yourself. Five, I will quickly cover. Okay. So, yeah, I'll just quickly tell you the answers to 5. Okay. The question says which of the following are true? L and NL both are closed under complementation. Okay. And this is actually true. In fact, any deterministic class is closed under complementation. So, L is deterministic, right? So, L is equal to co L. And say, for example, P is equal to co P. And EXP, anything that does not have an N, that is not non deterministic, is um, you can just switch the accept and reject, and then it's closed. And finally, NL is also closed. NL equals co NL. This is by this Immer-Menzel-Epstein. Okay, so A is true. Savitch's theorem solves reachability in order, log square, and space and polynomial time. Now this is false. Okay, this is false. It solves it in log square and space, but how much time does it take? It takes super polynomial. It takes n to the order log n. This is not polynomial. Polynomial means n to the some constant. So this is wrong. Okay, and using DFS one can solve reachability in polynomial space and polynomial time. This is true. DFS, it takes polynomial space. It takes polynomial space because you need to put that visited array and so on, right? So you need that visited array and queue and so on. Okay, and so yeah, DFS you can do it in polynomial space and polynomial time, and yeah, that is all I wanted to say. Okay, because this is an important part of space complexity actually, Savitch's theorem, and the trade-off between DFS and Savitch's theorem. Both solves reachability. Savitch's does better in terms of space, but it does worse in terms of time. DFS does better in terms of time, but does worse in terms of space. Keep that in mind, okay? And with that, I come to the end of this discussion. So, yeah. So, before we leave, I want to tell that there is a discussion, there is a final summary session which is happening on Thursday, 6 p.m. Okay. So, it's just a summary of all the concepts, and we'll quickly,
Okay,
yeah.
okay, sir.
Okay. So, yeah, right. So, we'll quickly revisit everything from top to bottom. Maybe I'll just give a few simple examples here and there, but it might help you in preparation for your test also, and it will be a nice recap. Yeah. So, any more questions, Bhuwana?
No, sir.
Okay.
Today, understood, sir.
Yeah. Today?
Today, all the things understood, sir.
Oh, thank you. Okay, good.
Thank
Okay
you,
then.
sir.
Prepare well
Thank you,
and
sir.
good night.
Thank
Bye.
you, sir.
Okay. Thank you.